Hello students and welcome to another video. I'm your teacher Mr. Flynn, and today we're going to be talking about states of matter. Okay, we are now in chapter 4, or unit 4, and we'll be doing 4.1 today. This is kind of a hodgepodge of a chapter. It gets into concepts that we're not going to cover, like gases and gas laws and pressure and all these other things. But I want to talk about some of the concepts in this chapter because I think it's foundational to your understanding of chemistry. Okay. And the first thing here is the kinetic theory and model for gases, okay? Because you got to remember, atoms, like we learned at the beginning of the year, atoms are always moving, they're always vibrating. And if they're moving, if they have more energy, they're in a gas phase. If they have less energy, they're liquid. And if they have less energy, they're probably a solid and they're vibrating, okay? So the kinetic energy is just basically referring to how fast atoms are moving. Okay. And if we look here, we have a box. And we can imagine that gases are perfectly elastic. They can bounce off the walls of this container without losing any energy, right? Because if we were to drop a ball and it bounces against the table, it's not going to bounce as high as it dropped because it lost some of that energy and it's in the bounce of the table, okay? And it's not going to come up as high. When we talk about gases, it's not going to be the exact same. Okay? And gases travel in straight lines. So these are the two big concepts when we're thinking about how atoms are moving in a gas phase. And that's about it. So you can kind of skip through these other things. In the notes on the book online, I've kind of cut these out. But in this section here, it should be in your notes or in your textbook online, the edited one that I've given you. Okay? And I kind of want to roughly talk about rotation, translation, and vibration, because there's three ways that molecules and atoms move. Okay, vibration is probably the easiest. It's just in one place and it's just kind of vibrating. Okay, it's staying in place. Okay, and if it's translating, it's moving in either direction, and then if it's rotating, it's turning. Okay, so there's three ways that they can move. As far as knowing how they move and knowing these terms, it's good to know, but it's not necessarily going to be part on your test. I'm not going to ask you to describe these, but if you think about it, you're like, well, if it's vibrating, it's staying in place. If it's translating, it's moving up and down, side to side, and if it's rotating, it's just turning like this. Okay? And down below, we can actually apply these three concepts to states of matter. Okay? If it's in the gas state, yes, it's vibrating, yes, it's rotating, and yes, it's translating, it's moving in all directions. Okay, so in a gas phase, molecules and atoms are all doing all three. Okay, in a liquid phase, it is vibrating because atoms are always vibrating. You notice that vibration is on all three states of matter here. We have it for a gas, liquid, and a solid. Okay, but when we start to get a liquid, there starts to be less mobility. They start to be a little more crowded. They tend to be attracted to each other because there's these intermolecular forces. We talked about this before. Water is kind of sticky. Water wants to stick together because of this hydrogen bond. Okay. But they can still rotate. They have enough energy to move around each other and rotate, but they're limited in their translation because there's other atoms there. This one can't just move to this spot because there's something here already. This one needs to move, so they're kind of limited on their translation. And when it's a solid, like this sodium chloride here, this table salt, it is only vibrating. They're not rotating, they're not translating, they're not moving around. They are locked in place. Right? It cannot conform to the bottom of a container. Because if you think about this water, it's conforming to this container. If I turn that cup sideways, the water would sink to the lowest point and it would kind of angle on this glass. It would conform to the container. This gas conforms to the container of the balloon. But if I have salt and I drop it in the bottom of this cup, it's just going to rattle around at the bottom of the cup because it's not going to be rotating or translating to conform to that container. Okay, so we're looking more in depth on these states of matter and how those atoms are moving. Okay, like I said, you don't necessarily need to understand these three terms, but when it comes to applying later bigger concepts, it's kind of like, oh yeah, well, I've learned about these three, I've heard of them, and this is how atoms move. There's just really three ways. And based on their ability to move, gives us different states of matter. And a big influence on that is intermolecular forces. So this one's talking about liquids and intermolecular forces. Okay, hold on just one moment. I gotta restart my screen. Okay. Sorry, screen was dying. Had to click it back on. Okay? So we have what we call a fluid, and down here I just want to talk about this because it relates to intermolecular forces. Here we have, all right, so this liquid isn't anything specific, it could just be water, and this liquid is, or sorry, this kind of gas is bromine. Okay, bromine's a very toxic element. We will never work with it in class. This picture will suffice. And if you notice, this is almost like a gas. So when you start to think about liquids and gases, the further you get along in chemistry, the area starts to get grayer and grayer about exactly what it is, what's defined as a liquid, what's defined as a solid, right? Because this is like a gas and you can pour it, but the reason you can pour it is because these atoms are attracted to each other as they're falling out of the glass, so they're sticking together, right? Because there's that dispersion force that's happening. And as you pour it into your glass, that dispersion force is there and it's holding those atoms together. The water is much stronger than the bromine atom, so it's going to be a little bit tighter. It's going to stick together a lot better than this gas is, almost this liquid gas. Okay, so gases and liquids can both be fluid, or something that is considered something that flows. I think the word is flows. Is it flows? So if it's flowing out of this jar or this flask into this beaker, okay, it has flow. It's a fluid. And we notice that the water is sticking together better because it has stronger bonds than the bromine does. Because this is hydrogen bonding and this is dispersion forces. And if you're not very good on your understanding, go watch the previous video. Okay? Oh, it's actually right here too. Here's the big three. If you need to pause this and take a picture of this, you can actually see these dispersion forces, dipole interactions, and hydrogen bonding. It actually relates it to its strength as well. Okay, so keep that in mind. All right. All right, I'm going to show you a picture here, and then I'll show you the chart. Okay. I want you to be aware of these four solids. Okay. We have molecular, ionic, metallic, and covalent. Okay. This covalent one's going to be the newest one that you haven't seen, but these other ones you should be kind of familiar with. Ionic bonding. Okay. You know this from your last unit from chapter 3. Okay, we talked about table salt and how it forms and some of its properties. It's most likely going to be solid room temperature. It's going to have a high melting point, etc. Okay, and there's a chart right here on this other page that I'll go through afterwards. Okay, molecular solids are basically molecules like water. Okay, in a frozen state. Okay, it's a molecule that's forming a solid. Okay, we know ionic bonds will most likely form solids. Okay. Metallic solids, metallic bonding. There's that sea of electrons going on inside all these cations here. All right, and specifically, I'm not sure what element that is, that picture is. I'm not sure what that is. You'll notice a lot of metals are probably grayish in color, but I have a few assumptions of what that could be, but I'm not sure. But anyway, not all metals are going to be solid. Like mercury is a liquid at room temperature. Gallium has a very low melting point. Okay, but if you got them cold enough, you put them in liquid nitrogen or something, they will become a solid and look something like this arrangement here, and they'll be solid. And then the last solid that we can talk about is called a covalent network solid. This is something like a diamond, okay, forming some of the hardest materials on Earth. And it's a covalent network of carbon atoms, okay, and they're forming these strong bonds, and they're sharing those electrons, okay. So over here is all the vocab. That I believe it's on your packet. You need to take those notes for it. And down below, this is the chart you need to be familiar with. Okay, this will be on your test. Okay, when we think about molecular solids, I want you to think of something like water, or carbon dioxide, or H2. Okay, these are your examples, and they don't conduct electricity, and they tend to be very soft, right? Because water is a liquid at room temperature. Their melting points are very low, and it tends to be atoms and molecules. And they have all three kinds of forces that are involved. Okay, ionic bonds, you can think of something like table salt. Okay, it's non-conducting, but if you put it into water and they separate into ions, they will conduct electricity. But for the most part, you can't just put a salt crystal and put a probe on each end and it won't conduct electricity. They tend to be very hard, right? Think of salt, right? It doesn't tend to break very easily, but if you took a hammer, you can break it, but it takes some effort to break those apart. They have very high melting points, okay? They are structurally ions, right? Because Na and Cl are both ions, and they're attracted to each other, okay, and they form ionic bonding. Okay, this should all kind of be a review for this one. The next one is metallic bonding. This should also be a review, okay? It tends to be just atoms, okay? We're not working with bonding, really. It's just atoms, not bonding, but we're not working with compounds or molecules. We're working with just individual atoms, and these atoms are just sharing electrons, okay? And their melting points vary. It could be thousands of degrees, or it could be mercury and it's a liquid, okay? The whole point of this table is to help you see compounds and see different atoms and think, oh, what could their possibilities be? Because I'm giving you a frame of reference, right? Because metallic bonds can vary greatly, but these other ones don't. Molecular structures tend to be low melting points. Like sugar melts at a low temperature. You can melt it on your stovetop. You can't melt salt at home unless you have a very high stove. We have to use a Bunsen burner to melt salt. And some other salts won't melt even with my Bunsen burner. Like magnesium oxide, I believe, won't melt with my Bunsen burner. It takes a lot of energy for that to melt. But metallic bonds vary a lot. Okay, it can be thousands of degrees to liquid at room temperature. Okay, and they are conducting because we have things like copper wiring in our house. Okay, the thing that will help you the most is pick one of these and use that as your frame of reference, and then think about what their structure is. What are they made out of? What's their melting point like? What's the hardness? Do they conduct, etc.? Okay, and then lastly, we have a covalent network. Okay, this is probably the newest one, but you can make this connection. Okay, because it's mostly just atoms. All right, they have very high. You can think of something like a diamond, okay, or graphite. So the reason the electrical conductivity it varies because a diamond doesn't conduct electricity, but graphite does because the way carbon configures itself, it's called an allotrope, and it can be in different frames, it can be in different structural units, okay? And that just means how they're arranged. Like this is a structural unit of salt. This is a structural unit of this. But we can actually rearrange carbon to look like different things. And it can form coal, it can form graphite, it can form carbon. It's a very odd element. So when you think of carbon, you got to think, okay, this is a different element, and it's not going to follow all the same rules as everybody else. And that's because it can form those special 4 bonds, okay? All right, and also quartz also follows this. This is something like glass and sand is made up of silicon dioxide. So its electroconductivity will vary because graphite conducts electricity, but diamonds don't. So it's going to vary, and it's very hard. Diamond is the hardest substance we know of on Earth. Okay, and the melting point is very high. Melting diamonds takes a lot of energy. Okay, and it's working with just atoms. Okay, bonding together to form this covalent network solid. Okay, so these are your 4 types of solids I need you to be aware of, and just to pick one of these and use it as your frame of reference. And that's it. If you use one of these, it'll be much easier to remember what each are. Just make that connection for these. Okay, I'll talk a little further on this. This necessarily won't be on your test, but it's kind of fun to know because it's something that we see in our daily lives. Okay, and what we have is 2 different concepts of a crystal and an amorphous solid. So down here we have a crystalline structure, right? I have the crystals in my class. You've probably seen them. They look like these, and they form these orderly repeating patterns. And if you look here at this glass, it doesn't form repeating patterns, and it's called amorphous, meaning it's not unified. Okay, I believe this black chunk of rock here, I think it's obsidian. I have some in my class that you could look at, but this is kind of like nature's glass, right? We have glass windows, and if you ever crack the glass window, does it crack like cleanly, like a clean line, like quartz will? No, it's actually going to shatter, and it's going to break off in all kinds of different directions, and that's because we heated the substance up and cooled it really quickly, and it creates this amorphous structure. And you may ask, well, why can we see through glass, right? The reason we can see through glass is because these structures here don't absorb light. Light is allowed to pass through these structures here, okay? But in this one, black actually has some probably imperfections inside this structure that absorbs light, and then it will re-release that light and it will look black. Okay, so it's just how atoms are interacting with light. If it's clear, they're not interacting with light. But if it's black, there might be some impurities in here that are preventing it that's absorbing that light and re-emitting it. If it's not re-emitting it at all, it's going to look black. Okay, if you have questions about this, come talk to me, and I can give you a little bit more of an explanation. But None of this will really be on your test, but it's just kind of a fun thing to talk about because it's something that we work with every day, like glass. And even, this could even include like pavements, like asphalt and other things. All right, so if we think here of like ionic crystals like salt, when we break them, the reason they have high melting points and it takes a lot of energy to break them is because when you break them, you have to put stress on them, and they're to a point where they're going to repel each other and they don't line up. Okay, and that's what causes them to shatter. They don't break cleanly like metal does, because metal, you can like tear it almost in some instances, and it will bend and break. Okay, so just keep that in mind, but it's not going to be on your test. Okay, all right. Thanks again for watching. Until next time.